Okay, hi there. In this video you are going to do a voltage sweep, okay, and study the characteristics of the transistor and a lot of interesting things. Let's just jump straight into it. So first of all, what I'm going to do is I'm going to take out the microphone. I don't want to delete it, but I'm going to just short it to the ground. So by connecting a wire between this and ground, virtually means the microphone is dead, doesn't exist. So let me just short it to the ground. Alright, so let's confirm that actually makes sense by running to see what happens. So now if I run and look at the input voltage, is just the bias point. The bias point currently at 0.69. So basically I have that. So that confirms that indeed the microphone doesn't exist. We could have just deleted it, but there's no harm in learning new things. Okay, so what I'm going to do now is to do a conventional voltage sweep. So right click and do DC sweep. So what I'm going to sweep is I'm going to take the voltage V1, so label V1, could have been BE, I have it labeled V1, so let me just keep it that, and I'm going to do a linear sweep. So I'm going to study the characteristics from 0 up to say 1 volt and see what happens to the transistor, and let's just increase it by 0.1. so let's see how the output behaves. Okay, so the input is just a sweep, so we start from 0 and keeps on increasing to 0.1. okay, just as we did to 1.0. sorry about that. Okay, now let's add another let me just take the output. Okay, so now let's study the two. We have the output voltage, and as at the time when the transistor's VBE was 0 up to 0.5, the transistor was basically dead. So this is what we call the cutoff region, because at that point there's no voltage coming in, because at that point there's no current, IC current flowing through. So the voltage here will be the same as the voltage here, because there's no voltage drop, because there's no current flowing through. So you can see the voltage on this point, which is node 2, will be the same, okay, which is 5 volts, just as the VCC. If I increase the VCC to 10, it will be the same 10 volts here across. All right, we can also look at soft saturation just above 0.5 up to, let's say, 0.65, 0.62, 0.63 thereof. Then right after that, the linear region begins. So the linear region shows that the current IC increases. As the IC increases, so let's just add the IC2. So you see that right there. So I1 is the collector current, which is flowing through RI1. That's the current flowing through the resistor R1, which is the collector resistor. Let me rename it RC to avoid confusion, and rerun it and ask for good. Okay, so we see that this just gives us the characteristics of the transistor, and that's quite interesting to note that at the point when the VBE is forward bias, current starts flowing, and as I increase the value of VBE, the IC current also increases. So the red line here is the collector current, and as the collector current increases, the drop across the resistor RC also increases, and as the drop increases, then the output or the collector voltage will also reduce. Just take your time, pause the video, make sure everything makes sense, and it's great to understand. Okay, so right after this point, when we move to a region called saturation, so beyond this point, even a further increase in the VBE no longer causes anything, because at this point now the current flowing through has caused the voltage of the collector to drop below the base voltage. And right when that happens, we know that now this region becomes forward bias, the collector base region becomes forward bias, and we leave the linear region, we go to a saturation region. So for an amplifier, I want to operate within this region here, where we have linearity and we can have linear amplification, which is very important. So when you start doing transconductance and small signal analysis properly, you know why linear region is very important to study these characteristics. Okay, so now let's keep the transistor the other way around. This time around, I'm going to change the sweep voltage. So I'm going to right click the DC sweep, and now what I'm going to sweep is going to be the VCC. So I'm going to sweep the VCC. I'm not sure if you are going to see this video right now, but I'm in the window. Okay, so what I'm doing now is I'm going to sweep this VCC from instead of 5, I'm going to sweep that from 0 to 5. So DC sweep from 0 to 5. The same incremental values of 0.1. That's fine. I don't think we'll change anything anyway. And I'm going to keep this fairly in the middle of the linear region. That's fine. So something like 6.5, 6.9. Let me just do 6.5. Mind you, are doing a particular transistor. So if you want to redo this experiment yourself, make sure your transistor is the 2N2222. Other than, because it has a different the properties might be different, so you might not get the same values. But if you want to do this on your computer, make sure you have the same transistor just for consistency. Okay. Alright, so now let's run and see what happens. So the first thing we notice is the VBE is constant. That's obviously, because now it's so obvious. Now I'm not changing, I'm not sweeping the VBE. I've kept that constant. What I'm varying now is just okay, so now this is what I'm varying now, the VCC from 0 to 5. Forget about the 5 that you see here. Internally, I've written the code to vary that. So this is the VCC. Okay, so now let's run and see what happens at the output. Okay, so now the output, interestingly, you see right from here up to somewhere here, after 6.5. Now what happens is that the base collector junction only becomes reverse bias when the collector voltage becomes more positive than the base voltage. The base voltage is 6.5. Remember, this is an NPN transistor. So if the collector becomes more positive than the base, it means it's reverse bias. And the condition for linear region or forward active region is that the base collector junction should be reverse biased. Okay, so what we do see here is that there's no output, nothing really happens until we get to that region, and there's an increase in the output. So let's take one more thing which is very important, is the current, how the current is also behaving. And this is the most interesting thing. Right up to this point, the current is just increasing. Then after this point, when the current becomes saturated. Okay, so after this point, the current becomes saturated. So here is the saturated region. Here is the saturated region because the junction is forward biased. The BC junction is forward biased, and right from here going, the BC becomes, that means the base collector junction becomes reverse bias, and we have some linearity. But this is the interesting thing. So from there, now there's no longer an increase in current. Don't get confused. I know it might be a little bit confusing why this region is not rather called the saturated region. There will be another video for that, to explain, to understand why this region is not called the saturated region but rather the linear region, because it looks like there's saturation here. So don't get confused, just take your mind off that and let's just concentrate on something here. This one of the most important use of the transistor when it's being used as a current source. So what is happening right now here is, after the collector base junction becomes reverse bias, any further increase in VCC no longer increases the collector current. So this makes the transistor behave as a current source, but it's not really ideal. You can look at it. If you look at it carefully, you can see that the current is not really constant. It's increasing slightly, okay, so let's increase the voltage sweep and see what happens. So let's just do up to 10. This transistor can take up to 30 volts, so let's do up to 20 volt VCC and see what happens after. Okay, so now it's clearer. So you see the current initially after the collector base junction becomes reverse bias. So now we are in the forward active region here. Now inside this region, see what happens here. The current is almost constant, and ideally we want the current to be a straight line. That would be a perfect current source. So I'm going to do something here. I'm going to put a resistor down here. You probably might not know what that is, but that's called a regenerated resistor, and let's see what it does. So R. Okay, so I'm not going to use any random value, say 500 ohms, and see what happens. Guess what? So see that it's almost an ideal current source now. So I have almost an ideal current source, and that's a good thing. But there are disadvantages. Headroom gets affected, because now the headroom will no longer be between 5 and 0, because the current, when it gets to this point here, the potential of the current is going to raise based on the value of this resistance. Of course, the more the resistance, the better current source you have, but you have shortened headroom. So there's a trade-off here when you put the emitter degeneration. This is just an introductory video. Just look at it, and we will look at, in future videos, look at how to get a better current source without using a resistor, and we might look at how the resistor really affects the headroom. So I want to keep this video as short as possible and interesting. So see you next time. Just rewatch it again, and I know everything will be good. Bye.